Welcome back, Algebra II students. I am now covering section 7.4. Again, this is optional. Just kind of keep wanting to point that out. So the last couple of sections we talked about, well, the last section, I should say, 7.3, we talked about geometric sequences and series. The section before that, we talked about arithmetic sequences and series. Today, we're going to just be talking about the sums of infinite geometric series. Now, in 7.2 and 7.3, when we had those formulas for sums of geometric series and arithmetic series in 7.2, they were for a particular number of terms that we were adding. So they are what we would call a partial sum. Okay, so a partial sum are the formulas that we've had up till now that are like S sub n. So you're adding up the first 5 terms or whatever. Sum of an infinite geometric series. Okay, remember those would be the ones that had the sigma that went from like I equals 1 up to infinity. Those would be an infinite geometric series, and we talked about infinite series back in section 7.1 if you remember. But here's the formula for that. And this formula is correct. There's no typos on this one. But here's the formula for infinite. Now, I want to also point out this last thing, provided that the absolute value of r is less than 1. Okay, that's a biggie. That formula only works if you have a fraction or decimal whose absolute value is less than 1. So it could be like a positive 1/2, it could be a negative 1/3, it could be an 8/9, it could be a negative 0.99, but it can't be greater than or equal to 1. So I want to point out this last little bit. If the absolute value of r is greater than or equal to 1, then the series has no sum. Okay, so if your ratio is greater than or equal to 1, I should say the absolute value of that, then it has no sum. Okay, now this is important because I have seen these time and time again on standardized tests like the ACT, where they will ask you for the sum of the sequence or the sum of the series, and I've seen students kind of struggle with those and just keep adding and adding and adding and hoping that it's going to get them there. And in some cases that will work. However, it's not very time friendly. So if you kind of know the trick, you know the formula here, it makes it easy to find. Okay, so this is kind of a visual example of this. You've got a couple of these on your homework, but I don't actually mind this visual example because it goes hand in hand with what we've talked about in the past when we were graphing different rational functions that had asymptotes. Okay, so look at this example 1. It says find partial sums. Consider the infinite geometric series 1/3 plus 1/9 plus 1/27 plus 1/81, blah, 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 blah. You can see from the pattern here that my r would be 1/3. That's what we multiply by a term to get to the next one. And it says find and graph the partial sums, okay, S sub n for n equal 1, 2, 3, 4, 5. So we literally have to find 5 different partial sums for 1 term, 2 terms, 3 terms, 4 terms, and 5 terms. Then describes what happens to S sub n as n increases. So what's going to happen as we add more and more fractions to that? What's going to happen to the sum? Okay, so you can kind of see the pattern here. S sub 1, of course, is 1/3, which is 0.33. And once again, you guys know this kind of drives me batty when our graphs don't match, but this does make it a lot easier to see. So on your y-axis, you see that we're counting by 0.1s, okay? And then on your x-axis, what they're calling n, we're counting by whole ones, okay? So if just the first term is a 1/3, so if we plot that point, that's here, okay? If we add the first 2 terms, that's 1/3 plus 1/9. we get a 0.444, not quite halfway between 0.4 and 0.5. Okay, if we add the first three terms, we get 0.481. Now, you could also use your partial sum formula. If you remember your partial sum formula, actually, let me write this over there, because some of the more complicated ones, this is how I did it. If you remember the partial sum formula, wow, that didn't come out very well. Okay, so a sub 1, the first term, times 1 minus r to the n over 1 minus r. Okay, so if you add the first three terms, you get 0.481. So you're getting closer to 0.5. Okay, if you add the first four terms, you get 0.494. That's really close. Okay, you add the first five terms, 0.498. That's even closer. Okay, what do you notice here? Okay, what you notice this dashed line. I'm going to put it in blue so it's a little easier to see. This is like your asymptote. Okay, remember when we were graphing rational functions, we could figure out the asymptotes, okay, horizontal and vertical. Anyway, asymptotes, okay. So from the graph, S sub n appears to approach 1/2 as n increases. Okay, so if we took the infinite geometric series formula, would we get a half? So I'm just going to actually like use this and test it out. Okay, so using the formula from up above. Now, the formula from up above doesn't have the little infinity symbol, but I'm going to put it down there so you know there's a difference. So the formula from up above looks like this. Okay, so for us, our first term is 1/3 over 1 minus, what did I say our r was? R was also 1/3. Well, this is 1/3 divided by 2/3, right? 1 minus 1/3 on the bottom here, 1 minus 1/3 is 2/3, right? And this big fat fraction bar is my division symbol, right? So 1/3 divided by 2/3 gives me 1/3 times 3/2. And of course, that's where my dead spots on my board are. 1/3 times 3/2. Of course, the 3's cancel. You get 1/2. So you can see graphically that that's where you're going. You can also see using the formula that that's where you're going. Okay. So I'm a visual person. You all know that. So I like seeing the graph, seeing where those partial sums lead to. Okay. All right, let's go down here in example 1. Now I kind of added the graph already, okay? But consider the infinite geometric series 1/4 plus 1/6 plus 1/16, or sorry, 1/4 plus 1/16 plus 1/64 plus blah, blah, blah. You can kind of tell here, what would my R be? R would have to be 1/4, okay? And we know, obviously, that this is my A1. Okay, now whether you use the formula or whether you literally just start adding them up, we're going to do exactly what we did in the one right above. The sum of the first term is obviously just 1/4, which is 0.25. Okay, the sum of the first two terms is 1/4 plus 1/16, or you could poke that in your calculator and you get 0.3125. Okay, the sum of the first three terms is 1/4 plus 1/16 plus 1/64. Poke that in your calculator, you get 0.328125. Okay, sum of the first four terms, 1/4 plus 1/16 plus 1/64 plus 1 2/56 equals 0.33203125. Okay, I literally poked these in my calculator and I didn't even round. Okay, And then the first 5 terms, okay? 1/4 plus 1/16 plus 1/64 plus 1 256th plus 1 1024th equals 0.333078125. Woo. Okay, now, a couple of things I want to point out here on our graph, okay? On my graph here, we are counting over by ones, okay? And so we are counting up by 0.05s, right? So this would be 0.10, 0.15, 0.20, 0.25, 0.30, 0.35, and so on. Okay, so if I'm plotting these points, let me do it in a different color. So one was 0.25, right on it. Okay, the sum of the first 2 terms was 0.3125, just above the 0.3. The sum of the first 3 terms was 0.328, a little bit higher, and then 0.332, and then 0.333. Notice again, this is my asymptote. This is the line that those sums approach. And my line here would be y equals point, actually I should do it properly. 0.3 repeating, or 1/3. Okay, now let's test that. So it says find and graph the partial sums, then describe what happens to Sn as this increases. So Sn approaches, 1/3 as n increases. At least that's kind of what it looks like to me. Well, let's test it out using the formula. Okay, using the formula for up above, so the sum of my infinite series would be the first term, the 1/4, over 1 minus r, which is also 1/4. So this is 1/4 divided by 1 minus 1/4 is 3/4, right? So 1/4 divided by 3/4 equals 1/4 times 4/3. Okay, again, 4s would cancel. So that equals 1/3. So yep, that absolutely works. Okay, so again, just a visual representation of those sums as we add more and more and more to it. Obviously, you can tell the more terms of this series we get, the smaller the fraction is going to be. Okay, and the more we add to it, the closer it's going to get to 1/3. Okay, all right, let's look at the backside. Okay, so now we're using that formula. Okay, sum of the infinite geometric series. Now again, what we need to know from the formula, here's the formula, it's on the front side as well. A couple of things. First of all, absolute value of r has to be less than 1. Don't forget that. Okay, absolute value of r has to be less than 1 for us to use the formula. Okay, so what we have to do, again, for the formula, we need, in order to use the formula, we need a sub 1 and r. Okay, so if I look here, we can tell just by the way it's written, this would be my a sub 1, this would be my r. Okay, and again, we're talking an infinite series, hence we have the little infinity symbol. Okay, so that's an infinite series formula, not the partial series that we've had the previous 2 sections with arithmetic and geometric series. Okay, so they're literally just poking in the formula. So this was my A1, this was my R. So 1 minus a negative 1/3 is 1 plus 1/3. So 1 plus 1/3 is 4/3. So it's 4 divided by 4/3, or 4 times 3/4. Again, these 4s would cancel, and you are just left with 3. Okay? Now, let's do a couple of these, and then I'm going to go back up to repeating decimals. But let's do some of these down here. So find the sum of the infinite geometric series if it exists. This is problems 2 through 5. So first of all, again, this is my A1. This is my R. Okay? So my formula, S equals, right? It is A1, that's my 3, over 1 minus R, which is 1/2. Well, that is 3 over 1/2. 1 minus a half is a half. So that is 3 divided by 1/2, which is 3 times 2, or 6. Now, I'm probably not going to write every stinking step out like that every time, but just so you can see, okay? Remember, when you're dividing fractions, you're multiplying by the reciprocal of the divisor. You flip the second one, okay? Now let's look at number 3. Number 3, again, here's my A1, here's my R, okay? So my S equals 2 over 1 minus negative 1/2. Well, that's 2 over 1 plus 1/2, which is 3/2. Well, 2 divided by 3/2 is 2 times 2/3. So that is going to give me 4/3. Do not round these answers. Leave them in fraction form. Okay? Most of these will be pretty simple looking fractions. I don't think you'll have any that are just too terribly ugly. But 2 divided by 3/2, remember, is 2 times 2/3, so that's 4/3. Number 4 down here. Now, this has to be my R. Where's my A1? Well, A1 here, there is no A1, so A1 is just 1, right? It's kind of missing from that. So my S equals 1 over 1 minus 0.9, which is 1 over 0.1, which is 10. 1 divided by 0.1, again, if you essentially move the decimal over on the top and the bottom, you get 10 divided by 1, 10. Now, number 5. I haven't really pointed this out in numbers 2, 3, and 4, but number 5, what is wrong with my R? There is no sum. The absolute value of 4/3 is greater than 1. So there is no sum. What that means is if your R is greater than 1, that means the subsequent terms of your series are going to get bigger and bigger and bigger instead of smaller and smaller and smaller. If the subsequent terms of any series get smaller, you can find the overall sum. It's going to approach some number, like an asymptote when it's graphed. If the ratio is greater than 1, then that just means that every term is going to get bigger and bigger and bigger. Okay, I should say the absolute value of every term is going to get bigger and bigger and bigger, and your answer is just going to just skyrocket. Okay, essentially, if it was always positive, it would approach infinity. But anyway, that is no sum. Want to point that out. Okay, because remember, one of the basic rules to use that formula for infinite geometric series sums is that the R, absolute value of R, has to be less than 1. Okay, so that one doesn't work. Okay, now let's go back up and talk about repeating decimals. There are several different ways to do this repeating decimal thing, but I really like this one the best. Years ago, I was helping my son do this, and they did it in a different fractional way. But once you understand series and sequences this way, I think makes a lot more sense. So what they've done is they have separated, in their example here, 0.888 into 0.8 plus 0.08 plus 0.008 plus 0.0008. Okay, the next term would have been 8 and then 0.1 to the 4th power. Okay, and so on and so forth. Okay, so that's where the pattern comes in. So what we have to understand here when we write it like this is that this right here will be your a sub 1 term, and that this right here is going to be your r every time. Okay, so then you use the formula. Okay, our formula for the sum of that, okay, there's the formula. So we're putting in 8 times 0.1. I prefer to literally just write it as 0.8. Okay, so 0.8 over 0.9. I know it doesn't really make sense when we're writing decimals inside fractions, but what you have to do then is get rid of the decimal points to keep it as a fraction. Okay, so then it's like you're multiplying the top and the bottom by 10 and you get 8/9. Okay, this process works really, really well. So let's look at some of our examples down here. Number 6. Write the repeating decimal as a fraction in lowest terms. Now, again, let me remind you, this is like 0.1 plus 0.01 plus 0.001, which is 1 times 0.1 plus 1 times 0.1 squared plus 1 times 0.1 cubed plus ... Okay, so my A1 term, okay, my first term is just going to be the 0.1. My R is also going to be 0.1. Okay, so because remember, this right here is my A1. This right here is my R every time. So if I poke that in my formula, I get 0.1 over 1 minus 0.1, which is 0.1 over 0.9, which is the fraction 1/9. Okay, that's how this one works. Now, let's look at 7. 7 is the same kind of deal here. 7, again, is 0.3 plus 0.03 plus 0.003 plus ... Now, that is 3 times 0.1 plus 3 times 0.1 squared plus 3 times 0.1 cubed plus ... Now, one thing I want to point out, 0.1 squared is of course 0.1 times 0.1, so that is 0.01. Okay, you'd have to have 2 places behind the decimal. Just want to point that out. Same thing with, 0.1 cubed is 0.1 times 0.1 times 0.1, which is 0.001. That's why we're increasing our exponent on our 0.1. Just wanted you all to kind of understand that. Now, again, so on number 7, if we use our formula, let me first point out this is my A1. This, again, is my R. Now, if you're just repeating a single digit, your R is always going to be 0.1. If you're repeating 2 digits, your R is always going to be 0.01. If you're repeating 3 digits, your R is going to be 0.001. Okay, so you'll see some of those here in 8 and 9 in just a minute. So now if we use our handy dandy formula, we have 0.3 over 1 minus 0.1, which is 0.3 over 0.9, which is 3/9, which is, I'm running out of room, 1/3. Okay, I kind of ran over the decimal point in purple there right above it. Okay, so number 7 would be 1/3. Again, anytime you have a fraction, you got to make sure it's in simplest form. And we know that 0.33333 repeating is the fraction 1/3. Now that's just kind of proved it. Okay, Now, 8. We've gone from repeating one digit to repeating 2 digits. So let me write this out. So this is going to be 0.71 plus 0.0071 plus 0.000071, and so on and so forth. So this is 71 times 0.01 plus 71 times 0.01 squared plus 71 times 0.01 cubed, and so on. Okay, so again, this is my A1, this is my R. Okay, so number 8, I'm going to have 0.71 over 1 minus 0.01. Okay, A1 over 1 minus R. So that is 0.71 over 0.99. Well, again, multiply top and bottom by 100, you get 71 over 99. Now, that fraction does not simplify. Okay, that's all you can do to it. 71 is prime. So, okay, now, number 9. Number 9, same kind of deal. Okay, so I'm just going to kind of jump to, this is 27 times 0.01 plus 27 times 0.01 squared plus dot, dot, dot. So my A1 is this, and of course this again is my R. Okay, so 0.27 over 1 minus 0.01. So this is 0.27 over 0.99, which is 27 over 99. I just quickly saw, oh, they're both divisible by 3. Okay, so that gives me 9 over 33. And then, oh wait, okay, both divisible by 3 again. I should have seen that the first one was divisible by 9. But anyway, you get 3/11. Okay, so that's how you turn repeating decimals into fractions using the formula for the infinite series sum. Okay, now let's move on to practice A. Okay, practice A. For the given series, find and graph the partial sums for, again, n equals 1, 2, 3, 4, and 5. So partial sums for the first term, the first 2 terms, the first 3 terms, blah, 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 blah. Okay. Describe what happens to S sub n as n increases. So first of all, I like to look at a series and kind of get all my information straight. My R is going to be 1/3. Okay. Now, on this, my first sum, so my S sub 1 is 1, 1/3. Okay, now one thing I want to point out here. Across the bottom, again, we're counting by ones. Okay, and going up, notice that little jagged line just means there's a break. We made a big jump. Okay, and then it looks like each subsequent line they're counting by 3/100ths, so 0.03. So this would be 0.41, 0.44, 0.47, 0.50. Okay, we're counting by 0.03 going up. I hope you guys can see that. So this would be 0.35. Don't know that we need it, but okay. So remember, 1/3 is 0.3 repeating, right? So 1/1/3 would be like right here, right above. Okay, 0.32. So S sub 2, my ordered pair would be 2, 4/9, and 4/9 is 0.4. Okay, so 0.4, that is like up here almost. Would actually be just a skosh above. Oh, nope, I lied. Put it on the wrong. Yeah, no, I didn't. 0.4 repeating, I'm sorry. It would be just a skosh above. I put it right on it, and it really should have been just a skosh above, because 0.44 is like 0.44000, okay? And this would be 0.44444. S3, okay, would be the sum of the first three terms. So we would go from 4/9, and I just poked these in my calculator, okay, 13/27, which is 0.481, okay? So 0.481 kind of puts me up here somewhere, okay? The fourth, well, the sum of the first four terms, I should say, would be the ordered pair 4, 40/81. And again, I just poked those in my calculator. And that is 0.4938. 4938. So we are getting pretty close to 0.5. Okay, and the sum of the fifth term, or the first five terms, I guess I should say, is 5, 121 over 243, which as a decimal is 0.4979. So we're getting even closer to 0.5. Okay, just below it. Now, what can you kind of tell here? Kind of looks like my 0.5 is going to be my asymptote. Okay, so it looks like S of n approaches, not 1/5, I was going to say 1/2 or 0.5, and S of n approaches 1/2 as n increases. Okay, now let's test that. I love how they kind of put these together. I'm going to test that because this right here is this same problem. Okay, the next section says find the sum of the infinite geometric series if it exists. So this is the same problem. This is our first term, A1. This is my R, 1/3. So we would have S equals 1/3 over 1 minus 1/3. Well, that is 1/3 divided by 2/3. 1/3 divided by 2/3 is indeed 1/2. Okay, so that does work. Okay, that would be my asymptote. Okay, now moving right along then to this section, let's do a couple others. Let's do number 5. So number 5 here, this, remember, is my A1. This would be my R. So the sum of the infinite geometric series would be 3 over 1 minus 1/3. Well, that's 3 divided by 2/3, which is 3 times 3/2, or 9/2. That would be my answer. Okay. 3 divided by 2/3 is 3 times 3/2. Now, number 9. Uh-oh. What do you notice about number 9? This would be a no sum. Why is that? Because the absolute value of 5 is greater than 1. Remember, that would be my R, right? My R would be a 5. In order for us to use that infinite sum formula, we've got to have the absolute value of R to be less than 1. And obviously 5 does not fit the bill there. Okay, let's do one more. Let's do number 11. So this would be my A1. This would be my R. So we would have S equals 2 over 1 minus 3/4, which is 2 over 1/4, which is 2 times 4 over 1, which is just 8. Okay? Now, number 12. Find the sum of the infinite geometric series if it exists. Okay, first of all, we would have to find R, right? It's giving us our A1. All of these, this is your A1, this is your A1, obviously, A1, A1, but we have to find R. Okay, so how do I get from the first term to the second term, from the second term to the third term, from the third term to the fourth term? So in this one, my R is going to be 1/2. 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. 1/8 times 1/2 is 1/16, and so on. So then in order to solve it, S equals 1/2 divided by 1 minus 1/2. Well, this is 1/2 divided by 1/2, which is 1. Okay. Let's look at number 15 and do it together. So number 15, what would be my R to get from 25 to 5? It's like we're dividing by 5, right? So as I look at this, this is divide by 5. To get from here to here, we divide by 5. To get from here to here, we divide by 5. Well, division isn't part of our setup for ratio, but that does tell me then that my ratio is 1/5. Okay, so that means my sum is going to be 25 over 1 minus 1/5. Well, that is 25 over 4/5. So we have 25 times 5/4, which is 125 over 4, or as a decimal, 31.25. So I would take either one. Same thing. Okay, now write the repeating decimal as a fraction in lowest terms. I think we did enough of these. I'm only going to do number 21 because I want you to kind of see what happens here when we have a number to the left of the decimal. Okay, so if I write this out, this is 43 plus 43 times 0.01 plus 43 times 0.01 squared plus ... Now, what we're going to do here is kind of separate this. We know how to find the repeating decimal for this part, so we're going to do that. Then we're going to add the plus 43 on later. Okay, so just for this part in the black, we're going to have 0.43 over 1 minus 0.01. Well, that is 0.43 over 0.99, okay, which is 43 over 99. 43 is prime, so there's really nothing we can do with that. But then we still have this plus 43. Okay, so two different answers here. You could have 43 and 43/99, or you could have the improper fraction, which is actually the way the book has it, 4300 over 99. Either one of those. Okay, 99 times 43 plus 43 is 4300. Okay, now I like this bobblehead one. It's the same kind of deal. So a bobblehead doll's head is pulled to one side and released. The head swings back and forth like a pendulum. On the first swing, the distance traveled by the doll's forehead is 20 millimeters. On each subsequent swing, the distance is 98% of the previous swing. What's the total distance traveled by the doll's forehead by the time the head comes to rest? So our setup here is 20 plus, said the subsequent swings were going to be 98% of the previous swing, right? So then the next one is going to be 98% of the second one. So that's 0.98 squared. Okay. And then the next one's going to be 98% of the previous one. So that's 0.98 cubed, and so on. Okay. Now, my ratio here obviously is the 0.98. Now, just like we did up above, we are first going to calculate this part. Okay. Then we're going to add the 20 onto it. Okay. So just doing this part, we get, well, 20 times 0.98 is actually 19.6 over 1 minus 0.98. Okay, which is 19.6 over 0.02, which is 980. Okay, now we take the 980, don't forget about the plus 20. Okay, and the bobblehead traveled 1,000 millimeters. Don't forget, on word problem, you always need to label it. Okay, hope that helped. These will be posted. This completes section 7.4.